Hi, hello everyone. This is the presentation on Apache Pulsar, which is the next generation messaging and streaming system. And my name is Matteo Merli. I'm an engineer at Splunk, and I'm one of the co-creators of Apache Pulsar. And my co-presenter is Karthik Ramasamy, which is a senior director of engineering at Splunk. This is the forward-looking statement that we may present statements on the future plans of the company and so on. So before starting talking about Pulsar, I wanted to have a brief introduction on messaging and streaming. We talk a lot about messaging and streaming and where Pulsar does fit in this space. So the first thing to realize is that there are kind of this duality. So typically when people think about messaging, they think about message passing between components or application or different services. So for example, like application A can send a message, and this message might mean, for example, like create a user account, and application B might take this and execute some action on it. On the contrary, like if you think about streaming, you think about having a stream data source of events that have happened already, pass that to message bus, and then use a stream computing system to analyze this event in real time. But you're analyzing things that already have happened. So you can think about messaging and streaming kind of like two different models, two different worlds, but at the end of the day, the infrastructure that supports them and that enables them is the same. And we can support both of them with the same infrastructure. If you're digging down on more like use cases, like for messaging, typically like you have like online transactions, integration between different components, and the main challenges for messaging typically are around latency, because there's a user waiting on that message to be published, for example, or availability, because if the system is down, the user will see a downtime, and data durability. If you say create user account and that message is lost, then that's a very bad user experience. And from application perspective, typically they require more advanced features like routing to different queues, or like having like a dead letter queues for retries, delays for messaging, individual ACK for each single message. On the other end, for streaming, it's similar, but the typical use case is that kind of like real-time analytics. And in these cases, the challenge is typically around throughput. You have a lot of events, and you need to be able to process them in a very efficient manner. You typically have like ordering requirements and stateful processing, so you have to send to write consumer, and also you have this duality between the real-time streaming analytics versus the batch. So you may have some batching system that is processing data in batch versus real-time. So at the end of the day, what we saw is that typically, like to have a complete data platform, you need to have three main components, and each of them has to be like very solid. So the first one is storage. You need to be able to store the data and have like a durability and scalability at the storage level. And then you need to have like a flexible messaging system on it to be able to easily ingest data and process data out of it. And finally, the compute, because like once you have data, you need to do something. You need to process this data and analyze it, process it, and modify it. So now we can, that we set the context, we can dig into which were the design choice for Pulsar. So the phrase tag that we typically use is that these are flexible pub, sub, and compute, which is backed by durable log storage. So we started by the log storage, and what gives us is the durability. The data is on disk and is replicated, both, and low latency. So we need to have like a lower than 5 milliseconds and 99 percentile. At the same time, we need like high throughput. So each partition has to be very scalable and available. So the system is this is the system, but we also want to design it in a way that is resilient, so that as long as we have nodes available, we can write on it. The write availability is very important. And cloud native. So we are able to scale up and down very, very easily. And that's a key requirement in the modern models of design, because now you can spin up new VMs or containers very, very easily. Continue on this. We have a unified messaging model. I'll talk a bit more what that means. We support like different semantics on a single topic, and we can scale to millions of topics. And we have a native compute framework, which is based on functions. And finally, Pulsar was designed from the ground up to be multi-tenant, to support different users with different workloads in a single cluster without any problems. And we also support replication, so that we can support applications that need to reside in different regions, in different zones. I talk about the messaging model, and that's a very basic characteristic here. So in Pulsar, you have topics, and you have producers that send messages to these topics. And now, the producer don't need to know how this data is going to be consumed. That is determined by your subscription. So subscription is a durable resource that you create on a topic, and that will keep your position on the topic. And there are different types of subscription for different needs. For example, you can use exclusive, which means that only one consumer is allowed to consume. You can use failover, which means that you have one active and multiple standby consumers that will take over in case the first one is disconnected. And the bit more fancier one are like the shared subscription. That means that you can add consumers on a single subscription, and each of them will receive a portion of the messages. So basically, you can scale up your consumption just by adding consumers without worrying about partitions or like increasing the number of partitions, because each partition will have can have multiple consumers attach it, and each of them will see different messages. And similar to that is kind of like a crossover. This is the key shared. So key shared means that you can still attach multiple consumers, but at the same time retaining ordering, in the sense that a message with the same key will route to the same consumer. So that is a very powerful way to scale up and order consumption. Pulsar client, we have like multiple client libraries. The official ones that are supported by the Apache project are like Java, C++, C, Python, Go, and Node.js, plus WebSocket, proxy, and so on. There are more that are like third-party libraries, like C#, there is Rust, and so on. Client library is very like high level in the API that is exported, supports like partition topic. There is also like a Kafka proper API, so that if you have a Kafka application, you can just immediately switch over just by swapping the jars to talk with Pulsar. There's batching, compression, encryption, and also end-to-end encryption to have completely to remove the encryption from the system, but just passing encrypted data from producer to consumers. So if we step back and take a view of the architecture of the system, this is like slightly different from the other messaging system here. We have this concept of two layers. So producer consumers will always talk to brokers, but the broker is a stateless service. It doesn't store any data locally. The data is stored in Apache BookKeeper, in the bookie nodes. These are the storage nodes. This distinction is very important because, first of all, it means that we can add brokers and bookies independently based on need. So typically, like you need more brokers if you are like more like a network intensive, or if you have many consumers, that's more like CPU and network bound. while book keys are more like the IO bound. So if you need like more writing power or more read power, you can just add more book keys, and you can do that on demand. That also means that in this case, that a broker is not owning the data of one topic, for example, so that you can quickly move topics from one broker to another. For example, like if you have if a broker is overloaded, we can just simply shift some topics from one broker to another, and we can react very quickly to changing in traffic patterns, and that is very important in a multi-tenancy system. And also mean that the bookie even are not the owner of the single topic. So we can also like ramp up bookies to have more IO if we need it. Since we talk about Apache BookKeeper, so this is kind of like a very important project for Pulsar. And what provides BookKeeper is a replicated log storage. So the API is very low level, is very simple, but the primitive is very powerful. So what gives you is like low latency durable writes. You can create a log and append the entries into it, and then close it, and then read it out. So, but what gives you is that this read consistency is highly available, and you can store many logs per node. You can even store like millions of logs per each node, and also provides IO isolation. IO isolation means that we can separate the write path from the read path in the bookies. So by that I mean that the write latency and the write throughput is typically not gated by the fact that there are reads on that node. So if you look inside one single node, you see that these two paths are separated. The write latency and throughput is only gated by the journal. So as long as we can write on the journal, which is dedicated to that, we are good to go. And irrespective of the fact that there are reads happening. And this is kind of like a very sophisticated architecture and way to use the disk, but that's how we can have a predictable performance that is not that does not rely on page cache, which is very unpredictable and can block threads at any point in time. So this is like gives like predictable latency and the highest throughput that you can get from the disk. And by the fact that we don't have any single file per single log, so the concept of log is logical only, we can scale to millions of logs per node. So we talk about BookKeeper and logs and so on. So for Pulsar perspective, a log is a segment, so it is not a topic. So what Pulsar does here is that if you have a single partition of a topic, it is not a single log, but rather is a sequence of logs, so a segment. So each log is a segment. So over time, we basically roll over these segments and create a new one and write in the new one. What happens is that basically we have this list of segments, but each segment, from a story perspective, is independent from the others. So if you have a cluster of n bookies, these segments will be spread across all the nodes. That means that I can just add one more bookie, and the new segments might go on that new bookie. That also means that if the most bookies are down, I only have 2 or 3 up, I can still write new segments. So my write availability is still there. So this is the same view, but compared with other systems like Kafka. So Kafka is more like partition centric. So a partition has to reside entirely on a single node, while in Pulsar case, what we do is that since we chunk in segments, like the size of the partition is unbounded, while in Kafka the size of a partition is determined by the disk size of one single node. So even if you have a 100 nodes cluster, your partition cannot be bigger than 1 terabyte if you have 1 terabyte disk. And then also like if you want to have new brokers take over, you have to do this rebalancing, which is copying all the data. While in BookKeeper case, what we do is just we simply add new nodes. We add new nodes, and new segments will naturally be created on the new nodes. because of this segment architecture, it becomes very natural for us to offload them. So that means that we use our tier storage architecture to basically move all segments to our cheaper storage. So for example, like if you are in a cloud environment, you might keep the list few hours or 1 day in BookKeeper, and the rest of the data can be pushed over to S3, for example, and that gives you like unlimited topic storage capacity and lower cost for like all the data. So that might be unlikely to be read, but you might want to have the assurance that you can read it if you need to. And basically, this is kind of like the true stream storage, right? So you can keep your stream forever and or for a very long time and very cost effectively. Continue on this. So if you think about the stream, the one of the important track is that you need to know which type of data is in there, right? So we have added a schema registry, which is based again on BookKeeper, the whole schema, and we enforce the data types on the topic. So if you have a topic, you define your schema for the topic. Basically, we can guarantee that the data being produced on that topic is conforming to that schema. And there are different strategies for like what kind of evolution to allow and what evolution to not allow, depending on the application needs. And we support JSON, Avro, and protobuf. And again, we can each application can configure its own evolution policy based on needs. And if you look at schema registry, basically like the way you declare the schema is it could be either like explicit, like using REST API to define the schema, or implicit by writing your application. So you can write in Java or Python, declare your schema basically. Like in this case, you have like a Pojo, which is my class, and you just say I want to use JSON with this my class type, and then you send objects. These objects will be validated that the type the schema for this object is the same or is compatible to what the topic already has, and the consumer can safely consume this data. Changing gears a bit, but this is very important, like for the distributed application. So the replication for Pulsar is like a first-class citizen. It was there since the very beginning, and what means is that you can have like multiple data centers and a Pulsar cluster in each data centers, and these Pulsar clusters are interconnected. What gives you is that you can publish and consume data from any of the Pulsar clusters in this case. So you always have the local publish latency, and you can decouple like the whole different regions. And it's basically like simply based on configuration. You just say that, okay, for these topics, I want them to be in the center A, B, and C. For this other topic, it might be only A and B, for example. And you can change it at any time dynamically. And what gives you is like is a very sophisticated like disaster recovery strategy, because these clusters basically are isolated. They don't depend on shared resources for availability. So if a cluster is completely down, the other one can keep going and accumulating the data. Once it becomes backup, the data will be replicated again. And one of the newest additions in this area is replicate subscription. So that gives the flexibility to have subscription that can be migrated at any point in time to a different cluster. So you might have, say, that you're consuming from cluster A, and cluster A is completely offline, and you can switch your application to consume from cluster B, and your subscription is being kept up to date by Pulsar itself. And there's already sophisticated mechanisms using markers and consider snapshot of messages across cluster. But from an application perspective, you don't need to do anything. You just have to specify that I want this subscription to be replicated, and then you can just switch your service URL and go to the other cluster, and your subscription state will be correct and will be there. So finally, multi-tenancy. We talk about multi-tenancy and how was that a single design characteristic of Pulsar. The main idea was that we don't need to have like each team to have its own cluster. That's very expensive. That's very error prone. That's very like operation intensive. And rather, like we wanted to have a single cluster that support multiple user and any workloads. So the main features to support these are like authentication, authorization baked in, the concept of namespaces, so that each team can use their own topics and their own namespaces, configure it in different ways without affecting how different topics are like how other tenants are configured, and having admin APIs for that each tenant can self-administer. And this at a logical level. But if you look at more at the IO level, there is more work to be done there, because like to support through multi-tenancy, we need to also provide isolation between tenants, and for that we need to provide isolation between write and reads. Then that's precisely what BookKeeper provides. The main issue here is to prevent different consumers to impact the system performance. So for example, like if you have a consumer that is catching up, it is reading from disk, that should not impact the performance of some other tenant that is publishing. And but the only way to guarantee that is that we have to have this isolation. Otherwise, you have things like in Kafka that one like a late reader comes in and is trashing the page cache, and that will basically impacting all the producer latencies and throughputs. Other than that, we also have like this kind of like soft isolation policies in place. Like we have storage quotas that once you reach your storage quota, you got like the data will be either like evicted or like producer will be blocked. Some action will be taken anyway. We have flow control at any place. Back pressure again at different levels at each level in the system. And we also have rate limiting, so we can like throttle the producers, throttle the consumers, depending on needs. And finally, like if all of these fails, we also have a concept of hardware isolation. So we can configure, for example, let's say that one tenant to be restricted to a subset of nodes, and that typically is done as a operation, like a last resource, so that you can take this tenant and avoid this tenant impacting other tenants or the reverse. And then with this, I will leave the word to Kartik to talk about the compute part of Pulsar.
Thanks, Matteo. So for the listeners, I'll be talking about the compute portion of the Pulsar. And so the compute portion of the Pulsar deals with something called lightweight compute. If you back up a little bit and see what are the different type of computes that we can do in a streaming system, there are 4 different types. One is the producer consumer pattern, where data is being produced, consumer computes whatever you want to compute with the data after it consumes the data. The second type of compute is called lightweight compute, where you do very simple tasks like line breaking, converting the data from JSON to XML, or route the data from point A to point B. So those are all very simple mundane tasks. So that is called lightweight compute. The third one is called heavyweight compute, which are gravitated towards more analytics purposes, where you have a multi-step DAG that takes the data and passes the data through these various different DAG nodes that process very sophisticated type of computes before it syncs the data back into the storage or designated destination. The fourth one is what we call as interactive querying on top of streaming data, where the data comes to a rest very, very quickly. And on top of that, you can do interactive querying on using well-known structured language like SQL. So Pulsar supports three different type of compute among the four different types. So which is the producer consumer, which already Mateo talked about, then the lightweight compute that I will talk about, then the interactive querying on the SQL. So in Pulsar Functions, which allows you to do the lightweight compute, we drew inspiration from lambda-like functions or serverless functions that people have taken inspiration from. So the user supplies a compute against a consumed message. It works on the function is written as in one of the popular languages and um, dispatched into the system, and then the data comes from the topics, and it's a function gets invoked, and the data is processed in the function, and the output is sent to an output topic. So this provides serverless functions provide the simplest possible API, which is then no SDK is required because we use the language specific function notation. Then there is a slight enhancement to the language function notation, for which there is some SDKs available for advanced features like state metrics and logging, especially if user defined metrics is needed for some of the compute functions. The and it is language agnostic. The Pulsar functions are language agnostic in the sense like you can currently supported languages are Java, Python, and Go. Easy to add more support languages, and it's pluggable runtime. It can be either run as functions can be executed within a broker if it is performance is of the highly critical, or it can be executed outside the broker as a process, then or you can execute on the context of a schedulers like Kubernetes or in the pods like containers. So let us look at the simple Python function. So you have the notion of a Python function called the process, which takes input as a parameter. Then you can return that input with the plus with the added value of exclamation. So which means the input string will be appended with an exclamation returned as an output. Similarly, in the Java style, you can derive from the Java util function and implement a method called apply, and the input for the apply method is a string input, and the output for the method is a string output, and the logic appends an exclamation to the input string and returns an output string. So uh, the Pulsar functions are very simple in the sense like the examples that I showed you does not have the notion of a state, in the sense like the data comes in and processed and data is put into the output topic. But in sophisticated functions like where you wanted to implement counters or some kind of aggregations, we need to store some kind of a state, and the Pulsar provides the inbuilt state storage because of the bookkeeper storage that we come underneath in the Pulsar functions. So the state is global and is replicated, and multiple instances of the same function can access the same state, even though they might be running on a different machines. And the function frameworks provides a simple abstraction of accessing the state and as well as updating the state, like get state, put state. For simple counters, we have a notion of increment counters. So the state is implemented on top of Apache BookKeeper, which there is something called a table service. And the BookKeeper provides a sharded key value store based on logs and snapshot. And the state is stored as a BookKeeper ledgers and WoW replicas that can be quickly promoted to leader because of the fact the data is replicated. If the node goes down, another node has to pick it up. So it can be quickly promoted to a leader of that particular state. In the case of leader failure, there is no downtime or a huge log to replay to bring that state back to the state it was where it left off. So like let us give an example of how a state looks like. So we have an API called context and Pulsar Functions. So you derive from the Pulsar function, and that it takes an input as a string, and then it's a void function which does not return any output. So the process is like the process is the name of the function, which takes the input string and the context parameter, and the string is split into words, and the word is counted. So like the context dot increment counter with a word with increment count of 1. So this increment counter is a stateful function which increments the counter at the bookkeeper level when the one multiple instance of the same function is run across several nodes. The counter is atomic, so that the count is accurate, and these counters can be accessed using a separate API which provides a key value like abstraction for getting those data, so that in case if you wanted to serve the data, the counters for a serving function or a serving application, you can use directly that API. So now, given we saw a little bit about lightweight compute in Pulsar, now let us look at how you can get data in and the data out of Pulsar. So there is a framework called Pulsar IO, which is based on Pulsar function, except the fact the source is input is some data. Sorry, the input is a void, and that output is the data directly to write into the topic. And sync is the input is the data from a topic, and the output is a void, which in turn has a logic of writing into their own syncs. So the Pulsar IO is a powerful framework on top of which you can write connectors very quickly. So there's a lot of built-in IO connectors that Pulsar comes out of the box, like Aerospike, JDBC, Twitter, Storm, Kinesis, RabbitMQ. Even we do have connectors into Spark, Flink, then Postgres, Debezium, for which we have the change data capture across several databases like Oracle, Microsoft SQL Server, MySQL, Postgres. There's a bunch of these connectors that are available that you can take advantage of out of the box. So then the second aspect of how to manipulate the data or how to query the data is based on the data stored in Pulsar. As Matteo pointed out, the data that enters into Pulsar is stored in BookKeeper based on the amount of retention period that you configured on. Now the question is, like, can we query the data directly stored in Pulsar? So that is what this discussion is about. So the Pulsar SQL is a wrapper that directly accesses the storage layer of Pulsar. It uses the Presto, which is the interactive query engine developed at Facebook. So it can query both historic data as well as real time. The reason why the data is real time is because the Pulsar's data that is coming in or ingested into Pulsar is synced with is immediately returned into BookKeeper, and within a few milliseconds the data is available for querying purposes. And since the SQL requires a schema over the data for querying purposes, the Pulsar SQL or the Presto implementation uses the schema registry that comes with Pulsar itself, so that it uses the Pulsar schema registry, Pulsar storage for querying the data. And you can also, because of the fact it comes with Presto, it can join with the other data sources. If you have MySQL data for which you want to join with the data that is in Pulsar, it's possible to do because of the fact Presto handles it, supports it. So Pulsar, the data, how the implementation happens is read data directly from BookKeeper and into Presto, and completely bypassing the broker. So that way, what happens is it's completely efficient. And in addition to that, the Presto shards are the shards of data that is distributed across the multiple nodes of BookKeeper can be parallelly queried, so that you get much more disk bandwidth, which means multiple shards can be processed in tandem, thereby giving a quick response time for the queries that you issue. So that is what many-to-many data reads means. Data is split even on a single partition, and multiple workers can read data in parallel from a single Pulsar partition. So as Mattia pointed out, it's not only the partition, it's single partitions and its corresponding segments are distributed across the entire cluster. So which means even if the partition is has to hit a single, even if the query has to hit a single partition, because of the fact that segments of partition are distributed across multiple disks, we can read them in parallel and process them in parallel. So that way, even if in the presence of data skew, the queries will run faster. And by default, it provides time-based index. We use the publish time to slice the queries based on time, so that the predicates could be constructed on top using that queries to reduce the data being read from the disk itself. So currently there are some work in progress to allow direct access to the data stored in Pulsar, and based on the Presto connector that we have done, so that computing frameworks like the Spark can directly do some of the batch computations on top of the data stored in Pulsar. So which means we can essentially marry the real time and the batch into one single infrastructure, the storage infrastructure. So that work is on the way, and it should be available anytime soon. So Apache Pulsar is a completely open source project, which was originally developed at Yahoo and open sourced 3.5 years ago, and it has been it has seen tremendous growth over the last 3 years. There are around 280 contributors so far in the GitHub. Then there are 30 full-time committers checking in, developing various features across different companies. There are hundreds of adopters, the companies that have adopted, and the GitHub stars is getting very close to 6K. And over 600 plus companies have adopted Pulsar, and it's growing at a faster pace. And some of the companies that is running Pulsar in production includes Verizon Media, which is Yahoo Japan, Tencent, and Splunk. Recently adopted Pulsar in a big way. Then Comcast, Nutanix, Overstock, Nerva, OVH Cloud launched a service based on Pulsar, and there is another commercial company called Kafkaish that launched a service based on Pulsar. OVH even contributed that protocol level compatibility for Kafka on top of Pulsar. Then Toast, which is a restaurant devices, serving device in restaurants, they are completely adopted Pulsar. So there's a list goes on. So that's all we have. Thanks for listening. If you have any questions, send us our way.